Well, the next talk will be given by Dr. Kelley, entitled Electric Field-Driven Instabilities in the Auroral Zone Ionosphere.
Our interest in measuring, is this okay? Our interest in measuring electric fields, both AC and DC, and our interest in anomalous resistivity has led us to investigate and search for electrostatic waves in the ionosphere. And our prime interest has been to search for the waves causing anomalous resistivity, but we've been inexorably led into the many electrostatic waves that are present in the ionosphere and low beta plasma, and have, we think, found some really nice waves of this type. Electrostatic waves have typical phase velocities the order of plasma temperature, plasma drifts, and thermal speeds, and hence they interact very strongly with the constituents in the plasma. So electromagnetic waves are nice and they travel very fast, but they don't interact so well with cold plasma, whereas electrostatic waves do. There are two ways of seeing an electrostatic wave, one through the electric field and one through the plasma density fluctuation, the same as there are two ways to see an electromagnetic wave. So we've also pushed our research efforts into looking at plasma density fluctuations. And there's an interesting relationship between the electric field and the plasma density fluctuations, which allows you to determine the real part of the dispersion relation. Since E equal minus grad phi equal minus I k phi for an electrostatic wave, and since phi is equal to delta n over n times kt over E, if you measure E and delta n over n, you can determine k as a function of frequency, which is the real part of the dispersion relation. We've done this for the two-stream instability in the electrojet, the auroral electrojet, and determined k as a function of frequency, and found that these waves indeed are traveling at the acoustic speed. And this has been published in JGR. And I bring it up to point out the power of measuring these two quantities at the same time and studying these instabilities. Today I'd like to talk about a electric field measurement only. This was made several years ago before we started measuring density fluctuations very well. And we have only the electric field in these measurements. However, the conclusions that I can draw from the measurement allow one to discuss what is going on in terms of instabilities in the E and F region. Excuse me. The interest of this conference may or may not be the fact that the instability I'd like to suggest we've seen is in the E region and couples upward into the F region along magnetic field lines and drives drift waves in the F region. The measurements we've made are all in the F region, and I believe they're drift waves. And I believe the drift waves go unstable on the density irregularities mapped up from the E region into the F region by a long wavelength irregularity in the E region. You cannot map short wavelength irregularities in the E region up to the F region. They just won't go. You have to have something like a kilometer scale size in the E region in order to map up to the F region. So what I think we have is evidence for drift waves in the F region, and I conclude backwards down to the E region because I know what the DC field and the density gradients were like in the E region. I'll conclude that the instability was the E parallel grad n instability in the E region. And there is some data by Balsley et al. Which supports this, which I'll bring out. Okay, could I have the first slide, please? Forward. Is that really as bad as? Oh, I see. This is the same data that Carlson discussed yesterday, and it's a rocket that flew up across several auroral forms and into the polar cap. And the slide is fairly busy, and it was essentially the same one that Chuck showed yesterday. So what you see here is highly irregular DC fields, polar cap, particle precipitation. There's arcs in here, and don't try to line things up yet because I have another slide. The important point is the irregularity. This is the wave potential difference at a particular frequency, which it turns out has no meaning at all because it's Doppler shifted in the reference frame of the rocket as a function of flight time. And one sees a strong band equatorward, it turns out, of the aurora, and then a deep null and some more noise again in between aurora, which I'll show later, and then a very quiet region poleward of the aurora. Okay. When one projects this down onto the aurora, as Carlson did, this is the same figure he showed. These are electric field, DC electric fields now. These are regions of F region turbulence. Here, and here are sort of boundary effects which which may be more complicated. There's upflows and even high ion drift velocities have seen parallel to B in these boundary regions. So I'm really more interested in the irregularity regions equatorward of the aurora and the lack of irregularities poleward of the aurora. One sees here the strong northward electric field pointing toward the auroral arc, and one deduces backwards from that it's parallel to the density gradient which points toward the arc. The correlation, and it is in this sense that the instability is electric field driven. And since the E parallel gradient instability is only present in the E region, one must conclude that if this is the instability, that it goes in the E region, maps upward along field lines. The density irregularities, long wavelength, map upward along the field lines, and then these density gradients in the F region are unstable to drift waves. Let me say first that drift waves in a collision-less plasma are unstable for wavelengths less than or comparable to the ion gyro radius, and that's the wavelength regime in which we make our measurements. It's the same wavelength regime in which 55 megahertz backscatter operates. It's this roughly 3 meter irregularity region. So the idea here is you have a two-step process. You make an instability in the E region, it maps upward into the F region, and drift waves grow upon that. And this process, I think, goes on in many regions in the ionosphere. I think it goes on in the equatorial spread F, for example, where you have a Raleigh-Taylor or some other mechanism that is the primary instability, and then you grow drift waves on top of this, which you then see with 55 megahertz backscatter. The relationship between the electric field and the fluctuation intensity is really strong. Here is, again, our irregularities at a different frequency, but it doesn't matter. This is the magnitude of the DC field perpendicular to B, and one sees this strong fluctuation amplitude. Then, just before we went into the arc, the field dropped down very low. It's hard to see. They run together. The field didn't go to zero, but it got very low, and the wave amplitude went down. And then in the region, again, where we see waves, you can see a almost one-to-one relationship between the wave amplitude and the DC field, as if there's a threshold for the perpendicular field in which the instability does not go. And then, again, poleward, there's just nothing in the irregularity. I'm getting all twisted up here. Let's turn it on. Okay, now why do we think these are drift waves? If you have a wave that's traveling at a very slow phase velocity in the plasma frame, and if you measure the DC field and the AC field, then since E is parallel to K, and if the phase velocity is very slow in the plasma frame, then the K is essentially parallel to the velocity of the rocket with respect to the plasma. You essentially Doppler shift the whole works, and the wave velocity is just the rocket velocity with respect to the plasma. But of course, that's what you measure with an electric field detector on a rocket. It's V cross B, where V is V rocket minus V plasma. So it's just exactly right. And you should find that the electric field is perpendicular to the DC electric field. The AC field should be perpendicular to the DC field. It shouldn't be isotropic. It should be only parallel to K, which should in effect be parallel to V, which is perpendicular to the DC field. I don't have a slide to show this. I have one in my briefcase. I didn't get it made in time, but the waves do show this characteristic. The fluctuating field is perpendicular to the DC field in the rocket frame. So I conclude that the waves are slow in the plasma, and that I can just Doppler shift the frequency I measure using the velocity of the rocket with respect to the plasma, not with respect to the Earth, to determine the K for the wave. So what I've done, first of all, I've plotted the spectrum in the rocket frame. Whoops. Oh, rats. Let me back up one step. The E parallel gradient instability should go on the equatorward portion of auroral arcs in the pre-midnight sector, because the electric field, the average electric field, is northward. This is the average electric field from 500 hours of balloon data in the auroral zone, which Forrest showed yesterday. And it's typically in the early evening hour it's northward, and after midnight it's southward. And this is exactly what Balsley sees in the E region. He sees equatorward of the aurora pre-midnight, he sees irregularities, and poleward post-midnight. So I think this just supports the idea that it's E parallel gradient in the E region for this particular instability. So, well, all right, a few words on drift waves. This is the potential. This is the spectra of the potential fluctuations in the rocket frame as a function of frequency in the rocket frame, and I've stuck in K rho equal 1 here. just to see where the frequency in the rocket frame corresponds to a wavelength such that k times the iron gyro radius is 1. Now, if I make the assumption based on the characteristics of the spin modulation of the data that the waves are slow in the plasma frame, I can convert into k space and plot the graph, the real graph. And this is the wave electric field in microvolts per meter times 1/2, which sounds funny, but it's right, for spectral density, as a function of wave number. This is k. And again, now I've stuck in k rho equal 1 here. And one sees a rise in the spectrum as one goes to larger wave number, smaller wavelengths, where k rho 1 is here. And I remind you that I said earlier that in a collisionless plasma, as we have here, the drift wave is unstable for k rho greater than or the order of 1. So it fits together fairly nicely. If people want to compare this to backscatter results, I've converted this into plasma density fluctuation in terms of percent, again, times meter to the 1/2, by assuming a plasma temperature and taking this equation over here and converting the electric field, dividing it by k to get the potential, and then that's on the left, the real wave potential, and the plot on the right is the density fluctuation as a function of wave number. And backscatter, 55 megahertz falls in here somewhere. So for example, the Hikamarka data or the Ben Balsley's portable 55 megahertz backscatter data that he did at the equator on several occasions falls in a wavelength regime comparable to these drift wave, these what I think are drift wave irregularities. That's all.
Yeah, Jan Siren. Mike, did you have any evidence of spin modulation of this of the AC electric field?
Yeah, I apologize. I don't have that graph. That's the whole idea in making this ansatz that the waves are slow in the plasma frame. If you see the DC field waving along at its spin rate, then the AC field is modulated at twice the spin rate because the waves are polarized in both directions, of course, because they're parallel to k and it oscillates. And you see the waves when the electric field goes through 0. That is, you see spin modulation at twice the spin rate, peaking perpendicular to the DC field. Yeah. You should do that.
Just a question that puzzles me a little bit. For these very slow phase velocities of the order of the thermal velocity, the wavelength then has to be equal to the Debye length, which is actually you can see it there. K, for example, for k equals...
That's for acoustic waves. These are not acoustic waves. The dispersion relation is that k V naught equals omega in the plasma frame. And V naught is really small. V naught is just the gradient length divided by the gyro radius times the thermal speed. And if the gradient length is a kilometer, you have a centimeter per second or something.
Well, omega is roughly of the order of the plasma frequency, right?
No, omega is very low. Suppose V is a centimeter per second, k is a gyro radius, and this is a tenth of a hertz or something.
Oh, okay.
They're really low frequency waves.
Oh, I see. Okay.
Their speeds are very slow. They correspond to the drift speeds of the plasma, not the thermal speeds. The drift speeds. And the drift speed, if you have a gradient that's some gradient length L, the drift speed is L divided by the gyro radius times the thermal speed. So if L is a kilometer and the gyro radius is a few meters, then you have 1% or 1/10 of a percent of the thermal speed.
Thank you.